I have very exciting news for everybody. Today, I want to tell you about chapter 17. And you know what chapter 17 is not about? Benzene. I'm done telling you about benzene. I don't want to say anything about benzene ever again. Actually, there are some benzene-like compounds, but we are not doing any more benzene-specific chemistry. After a long, hard slog of conjugated molecules, aromatic molecules, benzene chemistry, I think we all need some alcohol. Chapter 17. No, it's not on. That was my perfect setup. Come on. I was prepping for this joke in my office. That's right. You have to go to the bar for this one because you need to be ultimately familiar with ethanol. Chapter 17 is about alcohols. I'm going to just keep writing. You guys can just figure out what I'm. That's right. It looks beautiful. You know what I'll do is I'll just fold it up. I'll just do lecture like this. You guys can see it all right, right? Chapter 17 is about alcohols. And we're back and we're focused and we are doing organic chemistry. All of us, JJ is about to volunteer for all the try these today. So we're going to talk mainly about alcohols, but I also need to tell you about phenols. And this is where I have to do the come to Jesus that I've been lying to you about phenols. I've been calling phenol an alcohol, and I hate to tell you this now. Phenol is not an alcohol. It has actually very different reactions. It undergoes different reactions than alcohols. Alcohols imply a non-aromatic hydroxyl group. So something like a carbon, sp3, sp2 hybridized, non-aromatic with an OH attached. Phenol is, of course, a benzene ring. I know I said I was done talking about it, but only the hanger-on part, benzene ring with an OH attached to it. In both cases, I can refer to this group as a hydroxyl. So both alcohols and phenol have a hydroxyl group, in case you're wondering how to use that terminology. If we are going to talk about alcohols, we need to know how to name alcohols. That's section 17.1. So first up, we have talked about previously in OChem 1, primary, secondary, tertiary, quaternary carbons. Now we're going to talk about primary, secondary, and tertiary alcohols. You probably know where this is going, but we need to watch out for how many carbons are attached where the OH is. So the carbon bearing the hydroxyl group, we're concerned with how many R groups are attached there. This alcohol would be a primary alcohol because the carbon bearing the OH has one other carbon attached to it. A carbon with two R groups coming off of it, where the hydroxyl group is attached, would be a secondary alcohol. R can be anything. R equals carbon. Actually, R can really be anything. You can put R on a group and then underneath it say R is blah, 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 whatever you put. We typically use it for a generic organic, which is hydrogen or carbon. More often than not, carbon, right? If it's a hydrogen, you just put a hydrogen on there. I put three R groups on there. That alcohol would be a tertiary alcohol. And so it's the same thing that we have done before, but now we're focused on the carbon bearing the OH. When I say a primary alcohol, you'll find a carbon that has an OH on it. There will only be one carbon attached to that carbon. That's what we're worried about. As far as the rest of naming goes, we're going to follow the same conventions. We're going to just give priority to the carbon bearing the OH. If we call something an alcohol, that carbon is going to have the lowest possible number that we can give it. Step 1. Identify the longest chain containing a hydroxyl group. And then you're going to replace the E of the alkane with OL. For instance, the name of that molecule is what? Butane. The name of this molecule is butanol. Now I'm going to need to put more information in there in a little bit, but we'll get there. Namely, I need to tell you where the OH group is. But I'm just replacing the E of an alkane with an OL of the alcohol. Step 2, I need to number this thing. And before I told you just to number it to give it the lowest possible numbers. I still want you to do that, but you need to give the OH the priority. So in butanol, would I number this molecule from the left or from the right? From the right. That would make this molecule 1, 2, 3, 4. The OH is on carbon 1, so that is 1 butanol. I'll write that down here. Step 2 is number the alkane, or number the carbon chain. Not an alkane, you mean. Beginning nearest the hydroxyl group. One G, 2 Gs, begin. Beginning. 1 G, 2 Ns. That looks weird. Starting with whatever you want to spell it. Beginning closest to hydroxyl. Is it How I Met Your Mother, where like they say a word and they're like, oh no, it's like now it sounds weird to me, and they just say it over and over until it really like they can't say the word anymore. One person seen the show. Okay, yeah. Is that show too old too? Is it already come and gone? They've actually already made like a How I Met Your Father. Yeah, it's too old. Darn it. Step 3. Yeah. Step 3, we need to use our numbers to figure out what substituents are on this thing. So we need to number the substituents, write them alphabetically, and name the darn thing. Remember, I used to do this in 5 steps, but you guys are way too pro for that. So I think the easier way is just, let me show you examples and it should make some sense. What's the longest chain in that there molecule? Pentane. Should I number this pentane from the left or from the right? From the left. 1, 2, 3, 4, 5. I put circles around where there are substituents. What's at carbon 3? Methyl. What's the name of this one? Sorry, let me show you the way I annotate this back in OChem 1. At 3, I would put methyl. Now, normally I'd put 2 with the functional group, but I'm not going to do that here because I'm going to use that in the name of this molecule. What's the name of this molecule? 3-methyl 2-pentanol. I need to tell you where the OH is on the ring. If I said 3-methyl pentanol, you just close your eyes and envision 3-methyl pentanol. I know where the methyl group is. Pentanol is wherever you want to put the OH, right? So 3-methyl, hyphens between numbers and letters, 2-pentanol. Make sense? That's too easy. We need a challenge. What do you think the name of that molecule is? It would be if it was benzene. What is it? Cis what? I like that you got stereochemistry in there. So cis, the OH groups are on the same side. Cis, let's roll with this. Cis, they are on the same side. Hyphen 1,4. So let's just arbitrarily say that's 1, 2, 3. I don't know what's going on with my threes. They are not threes. 3, 4. Commas between numbers, hyphens between numbers and letters. Cis 1, 4. You could say dihydroxycyclohexane or cyclohexane. You're not going to like this. Diol. Now, why did I do that? If I said cyclohexanol, how many alcohols did I tell you were in that molecule? 1. I gave you 2 numbers, which means I need to say this is a diol. Notice I didn't drop the E over here because normally what we do is we replace a vowel with a vowel. Pentane ended in a vowel. All started with a vowel. So I swap out one vowel for another. That way it's not pentyol. When I don't swap it out, this one starts with a consonant. I leave the E, so it's not hexanediol, it's hexane diol, just to fit the English way that we say it. The other way that Peyton brought this up is also fair game. Cis 1,4 dihydroxy cyclohexane, although the way in blue is probably much more common that you'd see. Using all the same things that we've used before to name molecules. Questions? Now, for some of you, it's been a hot minute since you've done IUPAC naming. For the rest of you, you were in my class and you still don't remember it. I get that. This is covered extensively through OChem 1. I don't feel the need to really beat it to death in here. If this is not comfortable for you, make it comfortable for you. There are well-defined rules for naming molecules. I do not put a lot of emphasis on naming because it represents a very small fraction of what chemistry actually is. We need to know how to use words so we can write poetry. I'm interested in the poetry, not the words themselves. But there are some special words that I want you to know. So let me tell you about some common names before we get into sonnets. Oops, not everything in blue. But put an OH on this carbon, that carbon is special next to this group over here, which I'm not even going to call it by that name because we're done talking about a carbon attached directly to a is called what? Benzylic. This molecule commonly is referred to as benzylic alcohol. Similarly, if I have a 3-carbon unit with a double bond and I put an OH on there, this group, double bond, single bond, 3-carbon unit is called an, allyl. This is called allylic alcohol. What's the name of this molecule? Tert-butanol. Or the common name for it would be T-butyl alcohol. The reason I'm saying these are common names, the IUPAC name would be to put an OL ending on the alkane. So the IUPAC name for this would be tert-butanol, as Ren said. T-butyl alcohol is how you'll see most bottles of this labeled. It's used a lot in industries that say T-butyl alcohol instead of T-butanol. The reason for using common names like this, notice that they all say alcohol, makes it very obvious that there is an alcohol in the solvent that you're working with. If you're working in industry, you don't necessarily need to be so great at chemistry. Not being rude to my industry colleagues, but they do one thing over and over and over and over. So they need to make that process really efficient. Common names are meant to be widely used by people who don't necessarily do a lot of different types of chemistry. So you'll see common names used in industry a lot more than IUPAC names. If you were in lab, when I was putting the rotovapes together, you saw me playing with this. Oops, that's too many carbons. There. What's the name of this molecule? Has everyone seen the new rotovapes? They're so cool. I poured a weird green solution into the top of it, which is what? Antifreeze is formerly known as ethylene glycol. And then one more, just because I understand that like a couple of you are interested in like med school or whatever, I don't know, some nonsense like that. You will often in your biology classes experience over here. You just fill out the space, whatever feels right in your notes, wherever you want to put it. It's a choose your own adventure day in lecture. This molecule, which has a whole bunch of alcohols on it, it's a triol. Anybody know the name of this? It's very sticky. It's used to prepare slides pretty frequently. It's clear, but it's like viscous like syrup. Yeah, what? Glycerol. Has anyone besides Miss Monks used glycerol? Nobody's used that in lab yet? You will. I was going to say, a couple of you probably use this regularly. You can use glycerol when you're preparing, if you've run an agarose gel, you can use glycerol to fix the things into the agarose gel so they don't float away. It makes the lane really jelly and hold stuff in there. We don't use glycerol very much. It is a very important biological compound. So you attach things to the end of this. That's how you make a fatty acid. Questions about naming alcohols? I have to bring it up, but you already know the answers to these. I need to show you how to name phenols, which is how we also name. You just name everything as a phenol when there's an OH present. What is the name of that molecule? Named as a phenol. Paramethylphenol. The common name for this molecule is p-cresol. Any country bumpkins out there? Farmers' kids? You probably know this smell very well. It is the musk that pigs give off. Elephants also give it off as well. So if you've been to the zoo and you walk by the elephant exhibit and you're like, oh, I can't wait to see the elephants. There's a distinct like elephant smell, p-cresol. It's this very musty sort of smell. It's actually a pheromone. The elephants love it. If an elephant smells that from another elephant, it's like, what's up? I think pigs use something similar, but that very, like, if you've been around pigs, they have a very like unique pig smell, p-cresol. African elephants secrete this from the bulls, secrete this from their foreheads when they're in heat. If you happen to be wandering around the plains of Africa and you see an African elephant with like goo running down its face and a crazy look in its eye, you should get away from that elephant like as soon as possible because it's going to murder you in pursuit of a female. Life lessons from Dr. Green's class. Do I need to do any more phenols or do we get, you know how to name it, benzene rings, right? Let's do one more that doesn't have orthometapara. What's the name of that molecule? But where are the nitros? No meta. It's only for di-substituted. I got myself a tri-substituted benzene. 2,4-dinitrophenol. Where's carbon 1? Phenol is, of course, carbon 1 because we're naming it as a phenol. So then 1, 2, 3, 4. 2, 4 dinitrophenol. Sounds like you guys are picking this up pretty well. Just don't forget about your mono, di. You don't say mono, di, tri, tetra when you have multiple of a substituent. Do not say 2,4-nitrophenol. I know you could draw that structure, but when I say 2,4, I need di. Whatever. What's on carbon 2? What's on carbon 4? What's that? Which one versus the other way? What else would you call this molecule? Oh, if you wanted to call it nitrobenzene. Well, I'm calling it phenol because we're talking about phenol. We're crazy about phenols right now. This molecule could easily also be called nitro. It's a little messy though, right? Because then you have to be like, it's a 1-hydroxy, 2, 3, 4 nitrobenzene. So that's probably a less clean way of naming the molecule. Phenols typically are going to get a higher priority because they're more reactive. For chemistry, I'll show you in a little bit. Good on naming? You should expect naming questions. You have a quiz on Friday. Naming's part of it. You should not expect it to be the bulk of points on anything that I give you. Don't ignore it, but don't make it your everything. Students in this class tend to focus on naming when they're stressed out about other stuff because it's like this area they can control. They're like, everything else is horrible, but I know how to name, so I'm going to do that exclusively. That is not the path to victory in here. Right? So you need to know how to name to a point. That's, of course, not chemistry. Let's actually talk about the chemistry, but the properties of alcohols and phenols. First up, probably most important, is boiling points. Alcohols have higher boiling points than their alkane equivalents. Boiling points is, of course, BP. So what I mean by that is if I gave you a series of alkanes and then alcohols, you should be able to tell me about their relative boiling points. For instance, this molecule is, of course, drawn poorly and named what? Propane and propane accessories. Propane has a boiling point. Old people. 1, 2 old people. All right. -42 degrees Celsius. Propane at room temperature is a solid, liquid, or gas. I'm sorry, I got to give you both things. STP, standard temperature and pressure. Gas, right? So if I opened a tank of propane in here, gas would pour out and then we'd all die. So I didn't bring one as an example. But it's very much a gas because it boils well below room temperature. Propanol and I should put a 1 in here. If you don't see a 1 in there, it's assumed it's carbon 1, right? Because propanol tells you where the alcohol is. But 1-propanol has a boiling point of 97 degrees Celsius. Propanol at room temperature is a solid, liquid, or gas. Very much a liquid. And in fact, and for some of these alcohols, you can actually get them to be solids at room temperature. Now you're probably looking at this and saying, well, Dr. Green, of course propanol has a higher boiling point because it's got more atoms. This one has 3 heavy atoms. This one has 4 heavy atoms. And I remember distinctly that you told me that molecular weight influences boiling point more than anything else. And I have remembered that and owned that and made it part of the fabric of who I am as a person. I appreciate you remembering that, but not good enough. If I compare that to another molecule that has 4 heavy atoms in it, like butane, which, by the way, so propane has a molecular weight of 44. 1 propanol has a molecular weight of 60. Butane has a molecular weight of 58, right? So these are more comparable in their grams per mole molecular weight equivalents. But butane has a boiling point of -0.5 degrees Celsius. So it ain't the molecular weight that's causing propanol to have such a high boiling point. Excellent argument that you all just made, and I appreciate you making that argument. But why does propanol have such a higher boiling point? Loud and proud. Not less stable. Because of hydrogen bonding. When a butane runs into another butane, it has a very weak interaction. What interaction do alkanes have between each other? London dispersion forces, or the big boy, big girl way of saying that is van der Waals force. Van der Waals force is a very weak intermolecular interaction. You know, it's a super strong intermolecular interaction, hydrogen bonding. When a propanol runs into another propanol, we don't have to create these instantaneous dipoles where I kind of push the electrons aside from one to the other. This proton is especially positive, so it's got a large partial plus. That oxygen is especially partially negative. And so I can make this connection between these two. We typically use a dotted line, which is called a hydrogen bond. Hydrogen bonding is the strongest intermolecular meaning between two molecules force. So when a propanol runs into another propanol, they stick together really well, which means if I want two propanols to not just slide over top of each other, if I want them to go like that and turn to a gas, I've got to put in enough energy to make them break that hydrogen bond and move apart from one another. And they don't want to because they make lots of hydrogen bonds to themselves. All this cohesion, right? Sticking together. Water's really good at this as well, and adhesion, sticking to other things, but for the same reason, because of the bond disparity between oxygen and hydrogen. Not that you drink, but when you go grab your bottle of vodka and you pour it, that's ethanol. When you pour it out, does gas go everywhere and then you set the house on fire trying to party? No, you don't. You pour it out and it comes out as a liquid. Want to know why? It's mainly made of water, sorry. Also, hydrogen bonding. The ethanol in the bottle sticks together, which makes that otherwise very low molecular weight molecule a liquid at room temperature. It also means that it is miscible with water. Thank goodness, because otherwise you'd pour the vodka into something else and you'd have two layers. It would be lighter, and you go to drink it and you'd get nothing but alcohol on top and then wouldn't remember anything else in the bottle. Right? So hydrogen bonding allows these molecules to be both liquid and miscible with other things that hydrogen bond to it. Water being the most important when you're talking about ethanol. Questions about hydrogen bonding or vodka? I know more about hydrogen bonding. All right, something else alcohols can do is they can act as acids and bases. As a base. We could react this with something like HCl. And if I did it with HCl, it's really non-reversible. I'm going to put reversible arrows in here, but because I'm using such a strong acid, it really would just go all the way to products. I'm going to protonate. The oxygen is going to take a proton from HCl. Make this type of molecule, which is an oxygen with a positive charge. It's getting worse. Have you guys noticed this? Occasionally on your exams or quizzes, I'll put like a smiley face, but it'll like, I'll put it in red. But like, it won't look quite right when I do it. So I'm like, oh, I better fix it. And then the more I try and fix it, it just gets like scarier and scarier. And then eventually I'm like, screw it, just don't worry about it. Because I don't want you to see like a Joker smiley face and be like, what is going on with Dr. Green? This happens all the time. This type of molecule, I gotta fix the positive charge. It ain't right. This type of molecule is called an oxonium ion. Positively charged ions in this subject, in organic chemistry, in chemistry in general, have an ium ending. So if I say H3O+, that is called hydronium. It is water with an additional proton. It has a positive charge. Hydro, water, ium, positive charge. This is an oxygen with a positive charge attached to these. That's what we call an alkoxide, and I'll show you that in a second, but this has a positive charge, so oxonium. You're going to hear me refer to oxonium ions when we get into the chemistry of alcohols. That's why I'm showing it to you now. Alcohols can take protons. They're not very good at it. Oxonium ions, not the best. Why don't I like this oxonium ion? Yeah, it doesn't have resonance, but what else? It has a very attractive positive charge now, but it has a positive charge on what atom? On a very electronegative atom. Oxygen don't want your positive charge. Oxygen is very electronegative. You just said, hey, I found one of the most electronegative atoms in the periodic table. Here is not enough electron density. And oxygen's like, the hell, I had one thing I told you I wanted, electrons. Not great. Alcohols are thus much better at acting as acids. Oop, how about too many electrons? This one very much is in equilibrium. I'm having a hard time with my dots today. So if this acted like an acid, then water would take a proton from it, which would make oxygen with how many lone pairs over here? 3 lone pairs. And pray tell, what charge would that give me? A negative. Ooh, what else would I make? Well, sorry, here, we'll do this one first. This thing is called an alkoxide. IDE typically is reserved for negatively charged ions. We also use 8 for negatively charged ions. So if you see IDE or 8, be looking for a negative charge in there. Okay, now what else did I make? I took a proton from propanol to make this the way you would say this is propoxide. It's an alkoxide, so propoxide. Hydronium. 3. You know the name of that song. These 2 ions are the most common you'll see made for alcohols. Alkoxide is much more stable for the reasons that I just brought up. Up here, we have an oxygen with a positive charge. Not great. Oxygen can handle a negative charge much better. So alkoxides are much more common. What that should tell you is that the pKa of alcohols is relatively lower, much lower than its alkane equivalents. I can take a proton from this molecule very easily. Now, I will occasionally give alcohols protons. They make these high energy intermediates called oxonium ions, and then they go and do something else. So it's not impossible to make this. It still has an octet, but the positive charge is not ideal. But you know who's really good at acting as an acid? Phenol. Put this down here. It would fit a lot better there. If phenol loses a proton to water, then it makes what kind of ion? I know, a bad one. That one, what do you think that's called? It's a what? Yeah, phenoxide, perfect. So it is similar to an alkoxide, except this time it's a phenol, so phenoxide ion. Rin, did you go get a job at IUPAC and not tell anybody? Why is the phenoxide ion so much better? Lots of resonance. So here I've got an O minus, great. Good blood type too, right? Yeah, good universal blood type donor. The O minus can't move around anywhere on this molecule though. It's stuck on that oxygen. Now it's not a bad place for it to be stuck, but relatively over here, I have an O minus and tons of resonance. I can push the negative charge into the ring. Now, yes, that will break the aromaticity when I do that. That's not ideal, but it at least has the option to move that negative charge out around a bunch of molecules, a bunch of atoms, right? That'd be helpful if you're trying to take away a proton or something. Phenoxide ion, lots of resonance. You guys know what that says. Lots of resonance. I like that I committed to my big face here and I'm trying to write around it and I don't have enough space, but I'm not erasing the face. Lots of resonance means very stable, hence the face. So what's more acidic, phenol or alcohols? Phenol by a long shot. Phenols are much more acidic. Than alcohols. Which is why, if you were in my class for OChem 1 and you go back and look at your notes, you're going to be like, lies. Because one of the molecules I gave you when I had you identify functional groups had an OH attached to a benzene ring. If you watch that lecture or you look in your notes, you'll see me circle that and write alcohol. It is not an alcohol. It behaves very differently than an alcohol. It is much easier to take a proton off a phenol than it is an alcohol. The pKa of an average alcohol is about, alcohols generally, this is a rough estimate, right? Because alcohol, there's a lot of different alcohols, but alcohols generally have a pKa of about 16, give or take a lot. Phenols have a pKa of about 10, which doesn't seem like much, but remember, we're in log scale here. So that is 6 zeros. If you're making a 6-figure salary, that's a big difference for you. If you're making no money or $100,000, no, $1 million, right? 6 zeros, not 6 figures. So this is 1,000,000 times, a phenol is 1,000,000 times more acidic than an alcohol, which means the chemistry of those two molecules are very different, especially if you're trying to take a proton. Not only that, but we can play with the acidity of phenols with substituent effects. Substituent effects, because it's a verb, because it's a noun. The substituent impacts. If I take a phenol and I put a nitro group on it, who do I get to shout at? What do you think that nitro group? Thanks, Evelyn. You really missed out on an opportunity though to like give them the what for. What do you think that nitro does to my phenol acidity? Does adding the nitro group make this proton more or less acidic? Fight. I heard both. Who thinks more acidic? Who thinks less acidic? Who's not going to vote no matter how much I push on you? Yeah, everybody else raise your hands. There's a bunch of quitters in here. All right, the nitro group is an activator or deactivator? deactivator. That means it removes, I told you I wasn't going to talk about benzene, but here we are. The nitro group removes electron density from benzene. What am I doing if I take a proton from that alcohol? Adding electron density, right? I make an O minus. So it would help if I put an electron withdrawing group on this benzene. If a base comes along, it can take this proton. You guys ready for a wild ride of resonance structures? I'm going to take that proton. I'm not drawing any of the resonance structures. I'm going to take that proton and in one structure, push it all the way down. Actually, you do it before me. I want you to take that proton and push the electron density all the way down there. One structure. Go. Do it. You need 4 arrows. One structure. Put the negative charge on the oxygen and the nitro. JJ, you know who I'm going to for this, right? Actually, you know what? You should just come up here and draw it up here. Yeah, let's do it. JJ. No, it's gonna be great. It's gonna be great. There you go. Don't push the button when you write on it.
And the only reason I'm up here is because I wanted to try this.
Yep. Okay, so pull the proton. You're gonna break. You don't need to click anything.
Oh,
And you can touch the.
I can touch it?
Yeah.
Oh, wow.
I know, right?
That's cool.
Okay, so you're gonna break that bond between the oxygen and hydrogen.
I'm gonna break it.
You're gonna break it.
I'm gonna break it between the oxygen and the hydrogen.
Yeah, do it.
How do I do that? I don't know about this. Can I draw the other. Whoa, it just moved. I don't know if you want me to do this.
I do.
I don't think you do.
I do.
This is a mistake.
Okay, try again.
Try again.
Try this again.
I don't know about this.
So break the bond between oxygen and hydrogen. Where are you going?
I don't know.
On the structure.
On it. So
Yeah.
So just right there?
Yeah.
That one? How do I destroy
No.
it? Where does it go? Oh, down there, right?
There you go.
Sorry, took me a
Keep
little
going.
while. Okay.
Zero number 1.
And then doesn't this bond has to go down here, right?
It will, but not yet.
Not yet.
You know what, JJ needs some help. Which one's he gonna move next?
Yeah.
Yeah, the double bond that you're pushing towards, right? So that double bond to your right,
That one?
your other right. Oh, wait, sorry. your
Sorry.
right.
My left. I
Okay.
just
Used to be right. To your right.
my right is over here. My left. I
That
told
one.
you this was a mistake.
This one moves over.
This one moves over.
That one moves over.
Over there?
Yeah,
Did I-
Yeah.
Oh, there we go.
okay, then push the other one down.
This one's gonna go down to there.
It surely is. And then the next one from the nitrogen oxygen double bond is gonna go onto the oxygen.
The nitrogen and the oxygen is gonna go onto the oxygen.
It surely is.
There it is, right there.
Huzzah! Let's hear for JJ.
Wow, that was.
Sorry
Sorry about
plain
that.
one.
Yeah.
And so what that's going to give us then is a resonance structure where the nitro group has received the electron density that I pulled off of this ring. And so if you follow all the arrows that JJ put up here correctly, I'm going to put a carbon oxygen double bond there. Didn't touch this one, so it's still there. That double bond moved over to here. That double bond moved down to here. That nitrogen lost its double bond to the oxygen. This one didn't change. Charge. Still a positive charge on the nitrogen. Negative charge all the way down on the oxygen over here. My electron withdrawing group, remember, I would have made the negative charge up here on the oxygen. My electron withdrawing group pulled the electron density all the way off the benzene ring, all the way off the oxygen. The benzene ring is acting like a wire. This oxygen and that oxygen. Let me do this one more time. Watch what I'm pointing at here. The oxygen that's losing the proton and the oxygen of the electron withdrawing group are electronically connected. If something happens up here, the nitro group feels it and helps it, which means that it can help reduce the pKa. Paranitrophenol has a pKa of 7.6. I just told you that phenol itself has a pKa of 10. I dropped it significantly. Actually, sorry, JJ dropped it significantly when we put that nitro group on there. So the substituent effects of phenols can be really impactful on the pKa. And remember, as the pKa goes down, the acidity is going up. The opposite is true. If I put an electron withdrawing group on here, it would be less acidic than phenol, right? Because for the exact opposite reason, I'm making a negative charge over here. An electron donating group at this position would add electron density back to it. JJ. Yeah, bless you. Let's do one real quick since JJ was such a good sport about it. This is a question I love to ask on things like quizzes on Friday. Arrange the following according to acidity. And then, of course, I'll tell you 1 through 5, 1 being the strongest. You know, I'll put it in there about how I want you to fill this out. Number 1 is your strongest acid. Number 4 is your weakest acid. Who's looking at this and going, what's me? Methyl, CH3. I got 4 or 5 looks. I knew you were thinking about this. It's a phenol with an O me. One is the strongest acid. And if I'm feeling real spicy, which let's be honest, I'm feeling pretty spicy most days, I'll give you a bank of pKa's and then have you match them up based on acidity. So then I'm testing, do you know the relationship between acidity and pKa? But I don't have a bank of pKa's, so let's just do it 1, 2, 3, 4. Who's number 1? You guys are number 1. The strongest acid is not the first one, not the second one, third one. Why is this the strongest acid? 2 good reasons. 1, phenols are always stronger acids than alcohols. Why? Resonance. Phenols will always have more stabilized conjugate bases than alcohols. So all 3 of these are going to be more acidic than that because all 3 of these are phenols. That's the only alcohol in the bunch. So I know this is going to be the weakest acid because it's an alcohol. The rest of these guys are phenols. So now I need to differentiate those about which one of those phenols is the strongest acid. Peyton correctly, a couple of you correctly identified this would be the strongest acid for the phenols because that is an electron withdrawing group. That's number 1. Who's number 2? Phenol by itself, because this methoxy group is a activator, electron donating group. It's adding electron density in, which means this oxygen really doesn't want to take on a negative charge when this oxygen is supplying electron density from that side, because these are electronically connected as well, which means it is number 3. Ready to smell what I'm cooking? It's delicious. Have a great rest of your day. I will see you all on Friday, first thing quiz, and then we will pick up with the preparation and reactions of alcohols.